Welcome to the Deep Dive. We're here to cut through the noise and get straight to the insights. The world of AI, particularly large language models or LLMs, well, it's just constantly buzzing with innovation, isn't it? It feels like every week there's something new. And a lot of the research, centers on this core goal. Making these powerful models smarter, yes, but also much, much more efficient. Today, we're going to dig into some really cutting-edge research that tackles a critical challenge in LLM development. We're looking at how we can get these models to think or reason more efficiently, especially when dealing with really long stretches of information, either coming in or going out. Our exploration today is grounded in a fascinating new paper from researchers at Microsoft and Stanford University. It's called Decoder-Hybrid-Decoder Architecture for Efficient Reasoning with Long Generation. And it really offers a fresh angle on optimizing LLMs. So let's unpack it. Now, we know LLMs have these incredible, sometimes almost mind-bending capabilities, but they do hit some serious walls when it comes to efficiency, especially with, very long inputs or outputs. The main architecture we've all heard about, the transformer, it can get incredibly expensive computationally. This really bites when it's processing long contexts or, say, generating those very long chain of thought responses needed for complex reasoning. They're powerful, sure, but they cost a lot to run.
That's a really critical point. While we do have other approaches now, like state-space models, SSMs, and these hybrid architectures like USCO, they offer some computational wins, but they aren't the whole story. USCO, for example, it has this specific drawback. It doesn't fully solve the attention, memory, input-output cost problem during the generation phase. When the model is actually writing its response, think of it like a bottleneck. The model's trying to pull up relevant past info while creating new text. And this is a major hurdle for complex reasoning, the kind that needs those long, detailed outputs. So for LLMs to really shine at, sophisticated problem solving, the kind that requires thinking things through step by step, they need to do it without these crippling computational costs that make them impractical sometimes.
Okay, so the challenge is clear. Long reasoning without breaking the computational bank. What's the elegant fix proposed in this paper? You mentioned innovation. Right? This is where it gets really interesting. They introduced something called the gated memory unit, or GMU. The paper calls it a simple yet effective mechanism for efficient memory sharing across layers. Sounds important, but what's it actually doing under the hood?
Yeah, the GMU design is quite clever. You can picture it as a sort of smart gatekeeper inside the model's layers. It takes two main things: the current layer's understanding of the information, its representation, and then a condensed memory from an earlier layer. Then, using what the paper calls learnable projections, essentially, trainable parameters, it produces a carefully gated output. It's like it decides how much of the past memory is relevant right now. Conceptually, this mechanism is dynamically adjusting how different bits of information, the tokens, get mixed together. It's like a smart mixer, constantly tweaking the blend based on the current focus, making sure the right memory channels get the right emphasis. And the practical upside, well, GMUs save on both parameters, meaning a smaller model and computation compared to just using more standard attention or those MLP layers. It's a step towards leaner, faster models.
A smart gatekeeper, a real-time mixer, I like those analogies. So how does this GMU component actually fit into the bigger picture, into a full model architecture? The paper talks about a novel decoder-hybrid-decoder setup called SambaY. So SambaY uses something called Samba for its self-decoder. I guess that's the main thinking part. And then it cleverly swaps out half of the cross-attention layers and the cross-decoder part with these new GMUs. Cross-attention usually handles how different pieces of information relate, right? So this sounds like a targeted swap.
It is. It's a very strategic integration. And this architectural choice brings several pretty direct and powerful benefits. First off, SambaY significantly speeds up decoding the model, generates responses faster. It also keeps what's called linear pre-filling time complexity. Basically, feeding it more initial information doesn't cause the processing time to explode. It scales predictably, efficiently. And, crucially for our discussion, SambaY boosts long context performance. It gets better at handling those extended reasoning tasks. Plus, interestingly, it manages this without needing explicit positional encoding, which is how many transformers track word order. The overhead, the extra cost, is also really low. It just needs to cache a tiny bit of extra state information from the state space model component alongside the usual key value cache that transformers use. This reduction in memory I/O during decoding is a huge win, especially for the parts handling really long sequences. It drastically cuts down memory traffic. Instead of cost scaling with sequence length, it becomes almost constant. That's a massive efficiency leap for generating long chains of thought.
Right, so it's efficient when reading the input and when generating long outputs. That makes sense. Now, the paper didn't just propose this, they tested it thoroughly. They mention scaling laws, and this on P++ scheme for fair comparisons. Sounds rigorous. What did the experiments show about SambaY's scaling ability?
On the compute scaling side, the results were quite striking. SambaY showed the lowest irreducible loss, a technical term, but essentially it means it has the best theoretical performance limit. Its value is 0.58, lower than strong competitors like YOCO and Transformer++.
What this really suggests for you, the listener, is that SambaY isn't just a bit better. It seems fundamentally designed to scale more effectively, give it more computational power, and it gets disproportionately better compared to the others. It points to superior performance potential with larger compute budgets. Then there's data scaling. Now, it's true that a model like Transformer++, if you could give it literally infinite data, might eventually catch up to these hybrid models. But in the real world, with limited data, SambaY showed better scalability when you increase both model size and data proportionally. This suggests it's more efficient at learning from the data it does have, which is often the practical scenario. You get more bang for your data buck, so to speak.
Better learning from limited data, that's a key practical point. And what about specifically handling long information, like pulling facts from a huge document? Right, for long context retrieval, Samba and a variant called Samba+DA that uses something called differential attention performed better on tough benchmarks like phone book and ruler, and they did this even when using much smaller sliding attention windows, like just 256 or 512 tokens. It shows it can find the needle in the haystack more efficiently without needing to look at huge chunks of context all at once.
Scales well with compute, scales well with data, handles long context efficiently. Sounds great in theory and in controlled tests. But did they build a full-scale version? Does it hold up in a bigger, more realistic model? The paper mentions this prototype, 5-4 mini-clash reasoning, using the Samba+DA architecture. What did they find when they built that?
Yes, this prototype is where you see the real-world validation. It's a 3.8 billion parameter model, so not small, but not enormous either by today's standards. And it significantly outperforms a strong baseline 5-4 mini reasoning on really challenging reasoning tests. We're talking about benchmarks like Math 500, AME, GPQA Diamond. These require serious multi-step logical deduction, often in math or science. And here's a really interesting finding. 5-4 mini flash reasoning achieved these top results without needing any reinforcement learning fine-tuning. The baseline model did use RL. This is quite significant because RL tuning can be complex and resource-heavy. It suggests SambaY offers a more direct path to high reasoning ability, maybe simplifying the training process.
Wow, no RL needed for that level of reasoning. That's impressive. What about the speed and efficiency gains they measured?
The efficiency numbers are quite dramatic. They reported up to 10 times higher decoding throughput on prompts around 2,000 tokens long when generating very long responses, like 32,000 tokens. So imagine asking for a really detailed explanation or a long piece of generated code. This architecture could produce it potentially 10 times faster. They also saw a nearly 5 times speed up in just processing long contexts. These aren't just theoretical gains. They translate to much faster, more practical LLM reasoning, especially for those demanding chain of thought type tasks. It makes complex AI more usable.
And I have to mention, one of the case studies they included, it really stuck with me. It showed the model's internal think process. You could see it double-checking its work, reflecting, even backtracking if it hit a wall, and trying a different approach, like actual reasoning. And there was that example with the misspelled word strawberry. As to count the R's, it didn't just count the 3 R's written. It seemed to infer the user meant strawberry, and correctly answered 4 R's. That kind of common sense inference, especially without RL, is quite something.
That's a great example of the nuanced understanding it seems capable of.
They also did ablation studies, taking parts out to see what matters most. What did those reveal about why the GMU works so well here?
Those studies were insightful. They found that GMUs are effective with different kinds of memory sources, like attention outputs or MLP outputs. However, for retrieval tasks finding specific info, the type of memory matters a lot. The state space models used in SambaY have this natural recency bias, meaning they inherently pay a bit more attention to recent information. This turns out to be really beneficial for retrieving information that appears sequentially, like in a document or a conversation. The SSM memory complements the GMU's function for retrieval.
Okay, so the SSM memory source is a good fit. Anything else crucial about the GMU design itself?
Yes, one quite technical but critical detail emerged about normalization. They found that putting the normalization step after the gating mechanism within the GMU, using what they called normalized GMU or NGMU, was key for getting strong, long context retrieval. It sounds minor, but it points to the importance of maintaining associativity between the gating, deciding what's important, and the token mixing, combining the information. Basically, the order and interaction matter for ensuring information flows correctly for long-range recall. Fine-tuning these details unlocks the performance.
So wrapping this up, where does this leave us? It seems the introduction of this gated memory unit and the SambaY architecture isn't just another small tweak. It feels like a pretty significant step forward. It's making LLMs not just more powerful thinkers, but also much more efficient and scalable, especially for these really long, drawn-out reasoning processes.
I agree. This research provides pretty clear evidence for superior scaling, both with compute and data, and real practical efficiency gains. Particularly for those complex tasks needing long sequence processing and generation, managing memory and computation this well could really change how we deploy these models.
So as you think about the future of AI, consider this, a relatively simple concept, the gated memory unit, enabling models to reason more deeply and efficiently, potentially at greater scale. It's developments like these that could reshape how complex AI is built and used, making sophisticated intelligence perhaps more accessible, more practical, even where resources are limited. Something to ponder.